Good afternoon, everybody. My name is Seung Go. I'm an associate professor at Ina University in South Korea. I'm also main organizer of the 5th BrainLink X-ray Day program. First, I sincerely thank the all invited speaker and audience for joining us. Before we begin, please ensure that your mobile phone is set to vibrate or silent mode to avoid any interruption during this event. Then let's start today's talk concert. The topic of this talk concert is semantic communication for smart mobility. As you know, the semantic communication is one of the hottest research topics in wireless communication area, and we had the same event last year to discuss 6G semantic communication. Through the in-depth discussion during that event, we realized that semantic communication is not only the issue in standard wireless communication, and it is expected to affect the various research areas such as the computer vision, artificial intelligence, and autonomous control, which should call for developing new interdisciplinary research by interworking with the wireless communication. Smart mobility is one typical example, such as the autonomous driving and intelligent robotics. So this year, BrainLink Accelerated program will extend the last year program by distilling semantic communication from the perspective of the smart mobility. To discuss this topic, we invite the 5 top researchers, and we will have an in-depth discussion for this program. Before introducing our invited speaker, we will watch the introductory video about the X-Lab Day program made by the COPST.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X-Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X-Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. BrainLink X-Lab Day establishes a global science and technology network among overseas scholars and Korean researchers. And in 2022 and 2023, a total of 24 BrainLink X-Lab Day sessions were held in each technical field, with 787 participants, including 161 from overseas and 626 from Korea, building a global human network. Also, talk concerts, one-day public seminars, were held in collaboration with the 2 nights and 3 days of BrainLink X-Lab Day to enrich their experience. Professor Luke Pyeong-se Lee of Harvard Medical School, Professor Ji-Won Kim of MIT, Professor Andrew Goodwin of University of Oxford, Emeritus Professor Teruo Okano of Tokyo Women's Medical University, Jeffrey Newmark of NASA Goddard Space Flight Center Research Astrophysics, and Professor Dan I. Anderson of Uppsala University. The discussions will span 12 national strategic technology fields, pivotal to Korea's advancement, including the three game changers: quantum mechanics, nuclear technology, and AI. The event will see the participation of 40 Korean and international scientists and engineers. With two organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. And talk concerts will be held in collaboration with all BrainLink XLab Day sessions. The focus of XLab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each XLab Day session to ensure ongoing dialogue among attendees and promote collaborative research. COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations.
안녕하십니까. 한국과학기술단체 총연합회 회장 이태식입니다. 과총은 사회 참여 확대와 권익신장을 도모하기 위해서 1966년 설립한 공익법인으로서 과학기술단체 육성 지원과 다양한 정책 연구, 기획, 조사, 자문을 통해 과학기술 발전에 기여하고 있습니다. 저는 2023년 과총 회장으로 취임하여 새로운 도약을 위한 비전, 프라이드 코스를 선언하였으며 이를 실현하기 위한 운영 목표와 추진 전략을 중심으로 빛나는 100년을 향해 모든 역량을 집중해 나가고 있습니다. 더 나아가 우리나라가 미래 핵심 기술 분야를 선도하는 기술 주권국가로 자리매김하도록 국가적인 원팀 플레이를 이루는 데 있어 강력한 조력자가 되겠습니다. 대단히 감사합니다.
BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
Okay, let's move to our main part. Let me introduce our first speaker, Professor Riku Yanti from Aalto University in Finland. Let's give him a big hand. Yes, yeah.
Okay, yeah. Good afternoon, everyone. Yeah, so my talk will be about backscatter-enabled semantic communications and sensing, and maybe more about sensing than communications as such. And I come from Aalto University. We have a weird logo. We are supposed to pick one out at random, but usually I use the default in the slide set. So. And the reason for that weird logo is that Aalto University was founded in 2010 by merging Helsinki University of Technology with the Helsinki School of Arts and Design. And this design guys did the logo. We also have a business school, but we don't have any other fields, so no humanities or medical fields. And we are located in the capital Helsinki region of Finland. Okay, so I will first introduce what is backscatter communications, then talk about ambient Internet of Things, and then ambient backscatter, and there's ambient used twice in different meanings to make things clear. And then a little bit about how this thing could be utilized for semantic communications or sensing. Backscatter communications as a field is very old. The first backscatter communication device was made in Soviet Union in 1945, and it was a spy device. So it was this kind of a wireless microphone. So once it was illuminated with the carrier signal, then it captured the sound in a room and then transmitted that wirelessly out. So the Soviets gave a gift to the ambassador of Moscow in U.S. ambassador, and then started using this thing as for espionage. And it's difficult to detect because once you are not illuminating, it's completely passive device. And it's battery free, so you could use it very long time. So nowadays, the most common application of backscatter communications is RFID. So in RFID, there is some reader device that transmits an unmodulated carrier, and then the backscatter device either reflects the signal back or absorbs it. So it performs on-off keying modulation, and then the receiver receives the signal. The RFID readers are typically a bit expensive devices because it's kind of a full duplex device. But you can also implement RFID by performing frequency shifting, so then you don't have to have full duplexing. But then that requires more power from at the tag side. And RFID is widely used. I mean, it's ubiquitously used. So when you drive your car, probably the toll systems are applying RFID. In logistics, it's used widely. Or if you are a marathon runner, then your time is kept using this RFID tags. Okay, so this RFID has actually now, or backscatter communication, not RFID as such. Backscatter communications are the same principle of simple devices that communicate by either reflecting or not reflecting, has become once again like in the attention of industry. So this ambient Internet of Things is a term coined by 3GPP. So they are currently working towards a new class of machine type communication devices, which is sometimes called zero energy devices, so battery free, very cheap devices. And there is a ongoing work there to start utilizing backscattering in cellular setting. So now in that setup, the base station would be transmitting in downlink the carrier signal, and then the backscatter device would respond by doing frequency shift and transmit in the uplink band. So there is ongoing work in release 19. It's mainly driven by Huawei, but also Nokia is interested. So I've seen the Nokia backscatter testbed system in Nokia Bell Labs in Arlington. So that is something that is currently ongoing. It is mainly short range, so it would be like that in an industrial hall, or maybe in this room you would have had this kind of backscatter system. So it's not like a wide range system, but anyway. But it's not really green. Even though backscatter devices are energy autonomous, but you need to still quite a lot of power to generate the unmodulated carriers. So then this ambient backscattering, here the ambient refers now, in the previous case it was just ambient powered. Here in ambient backscattering it is ambient refers to ambient signals. So that the ambient backscatter communications is something that was invented by researchers at University of Washington in 2013. So instead of using this backscattering with unmodulated carriers, you could actually illuminate it with whatever signal. So the first ambient backscatter system was operating on TV bands. So TV transmissions are more or less continuous, although the amplitude is varying quite a lot compared to carrier, unmodulated carrier. But if you have long enough symbols, you could still use the same principle on those kind of signals as well. So reuse the spectrum for transmitting some low data rate sensor information. Okay, so you can do this also in a cellular setup. So base station is transmitting signal. So we want to utilize the cellular bandwidth to add some information to the channel by these backscatter devices. And the way we are looking at it is in-band backscattering. So this backscatter device is just making small frequency shifts. So the backscatter signal is kind of a additional multipath component from the receiver point of view. And you can do this either in uplink or downlink case, but what I will focus in this talk is the downlink, where the UE is the receiver. So it's receiving both the downlink signal from the base station as well as the backscattered messages. And the way to do this is that the backscatter device, since it appears as additional multipath component, so if it does some frequency shift with this, so then it looks like multipath component with Doppler. And the UE receivers in cellular systems, they are designed to tolerate Doppler because it's supposed to work also with high-speed trains. But the main use case of this kind of system would be maybe indoors, where the Doppler is quite small. So now there is kind of an excess bandwidth available in the channel estimator, where we can, which we can use to transmit this backscattered information. So the kind of frequency shifts that the backscatter DAX is doing is like few hundred hertz. And you can implement this in a standard modem with just software. So actually we have tested this kind of receiver with the MediaTek standard modem. So the idea here is that the modem is anyway synchronizing to the base station and doing channel estimation. The base station in LTE case transmits what these cell-specific reference signals. So these are OFDM symbols that are contain pilots, and they are transmitted for each antenna port separately. So based on those, the UE can estimate the channel. And now what we have been looking at that, okay, now if we estimate the channel, and then some of the channel components contain this backscatter signal, and then we can actually use that to receive it. And our backscatter device is an energy autonomous device, but in RFID, the system is harvesting the energy from RF, but in cellular systems, the signal levels at the receiver on the cell border is like minus 100 dBm or something like that. So it's not possible to harvest use that for RF energy harvesting. So we have a solar panel. But that device is very low power, so the modulator itself is consuming something like 165 nanowatts. It's a simple RF switch. And we have collaborated with Orange to test this. Orange is an operator in Europe, having the research facilities in France. So first we tested in the lab to see that, okay, the performance that we see is something similar to the FSK as we expect. And then those people in France, they tested with their own network. So there's a commercial LTE transmission happening, and then they're tested in a couple of locations indoors to see that, okay, you can actually demodulate this and detect the backscatter signals. And we have been doing the same kind of trials in our campus. So with the commercial base station transmitting LTE signals, and then we have reasonable coverage indoors, at least in our campus, to demodulate the backscatter information for very short range. This is a short range stuff. So we are talking about maybe a 1 meter range or something like that. from the backscatter device to the receiver. The distance from base station to the backscatter device is large. Okay, so how would that be related to semantic communications and smart mobility? One of the use cases that especially Orange have been working with, so this is actually one of the, these results are taken from their paper, is that if we have these kind of very cheap tags, simple backscatter devices, and we can put them indoors, so then we can use those as a kind of a reference points. So now when we are estimating the channel, we also notice that, okay, the proximity of a known reference point, so this is kind of the semantics that, okay, I know that I have to be in certain place of this building, so you can use it for indoor navigation, whether it's some human moving there or some robot, but so it's a kind of an alternative to this kind of a Bluetooth beacon-based navigation system, but this comes from free because it comes as a side information because when you are estimating the channel. So to conclude, there's ongoing work in 3GPP to use backscattering, but that is kind of just RFID on cellular bands. But you can actually utilize this kind of backscattering with the existing mobile communication systems, even without having to do any changes in the standard, just implement the receiver software in the standard modem. And then that allows us now to add kind of a semantics or get some information about the environment, like maybe identity of the object, that, okay, you know that you're close to some object, or this proximity information, or some sensor data, and that comes as a part of the channel estimates. So that concludes my talk.
Thank you for your nice presentation. Let's give a big hand. Due to the limited time, we received the Q&A during our panel discussion. So, okay, then let's move to the next invite speaker. Yep. Professor Mehdi Benis, University Oulu in Finland. Let's give him a big hand.
All right, so 15 minutes. So thanks again for the invitation. So I'm based 1 hour by flight from Helsinki, north of Finland. So today I'll be talking to you about something about semantic comm. It's been an evolving vision, hopefully trying to make more sense of this, I think, fundamental topic that we should pay more attention to, since it touches not only communication, but also robotics, machine learning, obviously, and others. Okay, so let's start from where we are today. So 6G promised a lot of things. This is a slide to bash a bit the ambition. So it promised to bridge the digital, physical, biological worlds. But essentially, the current visions of 6G, this is unanimous. The bigger, the better, more bits per second, more base stations are not sustainable. Everybody knows that taking 5G requirements of, let's say, reliability, going from 5 nines to 27 nines don't make sense. Robotics, if you talk to robotics, they will tell you that actually you can afford to lose a few packets. That's not an issue. AI plus 5G is equal to 6G. Well, we have to be careful for obvious reasons, I guess, right? So AI today is not only energy hungry, but is brittle, doesn't generalize, at best interpolator, right? So these are a bunch of numbers I think you're all familiar with, again, 5G to 6G, right? A new kids on the block, in fact, which I think could jumpstart 6G is resiliency. I will talk more about it tomorrow. It's not reliability and it's not robustness. It's completely different system design. In short, 6G today is basically 5G++, or this meme from internet, drink more coffee and make stupid things. Anyways, okay, so what do we propose? So here we try to flip a bit the paradigm to actually, instead of transmitting more information, can we transmit less, but instead reason and think more, right? To basically relax some of these requirements. 6G promised to be communication for machines, robots, right? So if that's the case, right, and interacting with humans, I think there is a very nice concept from neuroscience, Daniel Kahneman, who passed away maybe 1 month ago or 2 months now, the system 1 versus system 2. I really like this approach for many reasons. So system 1 is really all the machine learning you see today. So it's just interpolation machine. Okay, small data, big data, it doesn't matter. In fact, what's missing in many works, communication, machine learning, and so on, is the system 2, which is the one that allows you to plan, reason, right, out of distribution, think, right, compose few concepts together, come up with a new concept, and maybe test it in the real world. That's essentially in short, what we are missing today. So all the work you see today in the literature, including some of my group, are really system one. I mean, to simplify things, right? So of course, this topic is at the intersection of two kind of technologies. So there's a Paul Shannon. Some people don't like this word. I think it's fine. So the system, so the three levels of communication, right? So you have the level A, X is a message, encode it, MIMO, whatever. You get X hat, make sure X equals X hat. At that time, obviously, Shannon removed all the semantics, meaning structure, no memory, just replicate X from the sender to the receiver. I mean, the notion of also of information. We think information equals Shannon information. Of course not. I mean, there's biological systems, humans have a totally different notion of information. So yeah, that's basically the level A. So although in his famous paper on the bandwagon, I think some of us should read this, he warned us against using this level A, instead talking about level B, level C. So level B is really how to extract semantics, so data, meaning, right? That's level B. And level C, how the receiver or the robot or whatever is acting upon that decoded meaning. So here, of course, we add meaning, structure, memory. But here is where things get a bit interesting, at least from my perspective. I think it's a nice also intersection to allow later on. So here, what do we mean by level B? So some will just use their LLMs and apply it and use the output and call that semantic information. But here, what we really need to be thinking about is how do we learn concepts? I mean, these are agents, right? Learning concepts, abstractions, equivalence relations from sensory motor signals, right? And then how agents are gonna actuate each other so as to solve a task from the sensory motor signals, right? So we need to talk about agency. We cannot talk about passive agents in the world. That's not how we operate. I think this is fundamental to this topic. And of course, information is a vast. You have a notion of topological spaces, right? Shapes, right? People may be familiar with the invariants, Beatty numbers. These are, I'll cover them tomorrow, right? So the geometry of the data, right? The invariants allow you to encode this as an invariant to solve your task, right? On the AI front, I think everything is known. So basically what we do lack is is basically the reasoning part, the extrapolation, the system two, right? The ability to compose concepts, I think this is fundamentally missing today, including from the Benjio, Jean-Luc, and so on. This is very clear. So we could, of course, try to enrich maybe our models instead of just learning a model which is a function of the data and kind of minimal sufficient like VAE family or GAN or whatever. We need to inject more structure, right? Semantic communication is actually really about structure, right? So invariance, equivariance, disentanglement, causality, emergent. So this structure has to emerge via interacting between an agent and its environment, between an agent and other agents in the environment. Not hard coding that model. That's not how it works, at least for humans, I believe. So yeah, so basically this has to be done in a self-supervised manner, not supervised learning, where labels are given by outside observers. This has to be generated internally by the agent, okay? So of course we came up with the system one, system two approach here. I'm gonna go faster here. So system one is everything you see today. Let's take this example. So people work in age of information, right? For them, the age of a packet at the receiver is semantic information. Maybe, but that's system one, right? I mean, nothing new there. You could take also a picture of a dog here, map image to text. By the way, this appeared before the OpenAI was born, or at least was in stealth mode, perhaps. So you don't transmit the image, you map it to text prompt, you send the prompt to the receiver gets the prompt, generates a different dog. That's semantic comp for some people, right? We also looked at LLMs, but these are really just engineering hacks, nothing else from my perspective. So the semantic is really just the fresher, the better, perceptual compression, not abstract compression, and so on and so forth. So what we need, in fact, is really to look at different, maybe tasks. Now the task is really to reason, planning, right? That's not perception, right? That goes beyond perception, right? Then you could look at maybe trying to learn a protocol between robots in a factory. 6G promised that. Didn't even try to solve it, right? You could also have a base station with a bunch of users and trying to, under the ORAN, maybe architecture trying to emerge a different type of signaling other than 3GPP, right? And then the others are kind of straightforward. But from a more theoretical perspective, we need a theory of abstraction, must have. Otherwise, there's no semantic communication. How do you compose algebraically? Here, I mean, how do you compose shapes? How do you compose concepts? How do you compose agents, right? And of course, theory of interoperability. So this is just to walk you through a bit. So what we've been looking at. So questions, I think it could be the driving questions for semantic comp for students. for my group, this is what I base my research on. So how you learn concepts, of course, right? Then when you have the abstraction, use it for physical layer, Mac layer, and whatnot. Q2, how distributed algebraic structures, because this could be the syntax of different sensors, different models, different whatever, right? How can they communicate, right? What's the common mathematical structure they should project maybe their models onto, right? And then, of course, the planning and reasoning. So we looked at abstraction, of course. One recipe is never to learn a policy in the state space to the action space. That's model-free RL for students, right? You need to, don't do that, right? You have to learn it in the information space. And that's, of course, now open for any kind of abstraction you have in mind. You can abstract based on the size of your set, and features, symmetries, invariants, equivalent deformations, whole notions of algebraic topology here for us to explore. But we don't do it, unfortunately. So we looked at it from a, let's say, statistical perspective. This is a kind of learning a protocol between a base station and a user. We basically used the most naive way of abstracting. We took the observations of the agent, state, action, rewards. We fed them to a naive VAE, extracted the latent representation Z, and just generated signaling, right? And picked up the best signaling. This was shown to outperform one baseline, which is MAPO, without abstraction, because we obviously knew abstraction is going to help us, obviously, to generalize, right? We also looked at something more principled. This is basically about learning concepts or semantic compression through the lens of topology, right? So there's a notion of shapes again. You could say that two, maybe, for example, an example here, these are different fields of view, right? They may look different, but in fact, they are equal, they are equivalent, right, in terms of their what we call, this is a persistent diagram. It kind of calculates the invariance of your field of view. So that's compression for me. That's kind of what I'm trying to push for here. These are just some results here to show comparison with other type of so-called semantic information like VAE. VAE, the problem with VAE and other families is they lack structure. That's the big problem they have, right? But of course, we shouldn't forget that there is a lot of relevance to look at formal methods, logic. These are very important for many reasons. We don't even talk about them. So here, for example, we need to learn maybe to compress mathematical theories of the world. By world, I mean external environments, right? And then we have now, this is program inference. It's not the statistical inference, such as maybe free energy principle or other type of inference. This is totally different family of inference, right? You could also look at it from this toy here, example. This is System 1+, so we looked at it from, let's say, maybe agentic ways. You have the perception module, the actor module, right, the policy. So model-free approach plus abstraction. So for us, we looked at only state abstraction, but don't forget you can look at state, the whole trajectory, right? State, action, reward, abstraction. But we didn't look at its planning. And I told you planning and reasoning is a fundamental piece of semantic communication. And it's related to what we call the world model. So world model is right now very much a hype. If you follow Yann LeCun's architecture, JEPA is one of them. So here the idea is you need to learn a world model from data, right? Which is against generative AI. Generative AI is basically to reconstruct maybe the input. World model is to understand the input. There's totally different approaches. And then when you do that, you can now run, let's say, counterfactual questions. What would have happened if I choose a different action or depending on your use case, right? This is missing today in many papers, but of course, this is just piecing things together, right? In closing, of course, Semantic Com, I think, is a game changer. There is no doubt about that. System 1, System 2, I hope you see the difference here. What we do lack, how we should properly formulate it through agency, of course, and maybe transition systems, if you're familiar with this. Also, planning is a key part, world models. Information, don't be, narrow-minded in terms of, I was narrow-minded in terms of Shannon, but Shannon is a tiny dot in the ocean. You have other types of informations that are very common when you talk to roboticists, for example, right? Yeah, and maybe just saying again what I just said, interoperability also, principles are missing. We talk about them, we never formalize them. I think we could do it through this approach here. Finally, there is this resiliency, a new kid on the block called resiliency, and I think it's if we understand it well, it can completely dwarf all the requirements we see today in 6G, because here the idea is bad unforeseen event will happen. Okay, this could be a military setting, I don't know. But how do you design a network with that in mind, right? So here you can, again, get inspired by the brain. You have this notion of plasticity, right? How you can modify or your structure, right, of the world, basically. And then, of course, you have the functional adaptation. Anyways, yeah, this is basically what I wanted to say. Thank you very much.
Thank you for your nice presentation about system to semantic communication relevant to world model. Let's give you a big hand again. Then let's move to the next speaker, Xuyan Yu, a principal engineer with Huawei Technology.
Thank you. My name is Xuyan Yu, and I'm from the Theory Lab at Huawei Technologies. So as the title suggests, I'll be talking about evolving multimedia compression in the era of AI-enhanced communication. So I will talk from these three perspectives. First is from the perspective of large language models, and we study semantic compression with the aid of large language models. And secondly, I will talk about perception-centered image and video compression using also AI method. And lastly, I will talk about generative modeling in general for semantic communications. So first, I'd like to give a brief introduction of the semantic compression. So as Professor Bennis has talked about in the previous talk, so when Shannon and Weaver first approached the mathematical modeling of communications, they proposed these three levels of communication. So previously, we were at level A of communication, where we consider the accuracy aspect of the communication. But right now, what this community is going to push forward is that we want to study the semantic problem, which consider the meaning of the transmitted symbols. So firstly, I will talk about large language models, because nowadays with the aid of large language model, we can actually understand the underlying meaning of many textual information. So as a motivation of this problem, we can see from these two studies in 2024, or from this year's research, on the left-hand side, it says that GPT-4 has passed the Turing test, which says that GPT-4 actually has the capability to understand what human communication, or it has some capacity of understanding the textual meaning. And on the right-hand side, it says that GPT-4 has exceeded the average performance of graduate-level courses. So it means that with some fine-tuning method, or with excessive training, this GPT system or this large language models is capable of doing reasoning, or it can reach the kind of expertise as a graduate student level. So I will be talking about our recent paper on scaling laws of large language models, which has been published in arXiv this year. So with scaling law, what we want to study is the relationship between the training data and the computational resources and the model. These are important because when you start to train a model, you want to know what data is available for you to train the model, and also your computational resources. And the scaling law says that if you have more and more data that is available to you, and using more computational resources, actually you can train a larger and better model. So that caused a problem, because right now, as this research have shown, with training large language models, it has already caused a lot of carbon emissions, also energy consumptions. So these people from industry has predicted that in the future, what is going to be a bottleneck is the energy. right? So they draw this conclusion because they have the scaling law for neural language models. This study is pioneered by some researchers in OpenAI. So what their theory is that they feed this curve, they call it empirical scaling law, and it is actually known as the chinchilla scaling law. What they've done is that they train a lot of models and try to feed this exponential expression, where L is the training loss. We want to minimize the L through training, and N is the number of parameters of the model, and D is the number of data that is available. So they train a lot of model, and then they feed this curve. So their conclusion is that we have these scaling laws. So if this scaling law is true, then we can predict that in the future, if we have more computational resources, what is going to be a bottleneck is actually going to be the data, because we will soon run out of high quality data. Right, so next I will talk about our model. So it all come back to the training of large language models. So large language models are trained with a task called next token prediction, where you have some tokens, and then you want to predict the next tokens. In this case, the green letters. And then there will be a ground truth, and then you compare the prediction and the ground truth, and then it will give you a loss. So this is similar for images and videos. You can turn the images into tokens and then do the same thing for prediction. And so we model these large language models as associative memory, which is different from other memories in computer systems. So associative memory is content addressable, which means if you have a large system that memorizes some patterns, we want to curate the system so that it will return you the closest pattern with the true memory. So it's kind of like a code in information theory. You have a query, probably is correspond to the first few tokens, and then you retrieve from the memory what you want for the next tokens. And then in this paper, we actually proposed a new energy function for the system. So it's an energy-based model. We propose this energy function as opposed to previous research. Our energy function is actually simpler, and it has better performance in terms of interpretability. We can interpret this energy function using this auxiliary function, which functions as a nearest neighbor search over the set of patterns. So with this, we can conclude that our proposed energy function is a smooth surrogate of the nearest neighbor search. So we can model the transformer model as we can model the transformer layers using the search algorithm, so which gives us very nice results we will be talking about tomorrow. So we also, using this model, we can analyze the loss of these large language models, which we have listed a few here. We can see that the loss is about 2 point something. So there's a theoretical reasoning here. So some outlook and challenges for large language models. I think there are two main issues here. One, we want to train better models, and the other is that we want to use pre-trained models more smartly and responsibly. So this is because we already have a lot of pre-trained models. We want to take advantage of these available to us. So transformer have some intrinsic constraints. For example, it has a limited context length. And also there's the problem of hallucination. So here we can see that with different models, we have different context windows, but most base models are have a context window of 4K or 8K. And this is actually a very important parameter for how good the large language model is. And the hallucination is to say that if you ask the large language model a question, then it may give you some answer that is incorrect, but it seems to make sense. So that's the problem of hallucination. So these are two main issues with current large language models. So in this paper, we deal with the limited context window problem. We design a semantic compression module before we enter the sequence into the large language models. So this is motivated by the problem of source compression in information theory, where given an excessively long sequence, you want to be able to input the sequence into the large language models. So what source compression does is that it removes the redundancies in the information. So here, similarly, we can remove the redundancies in terms of semantics. So we try to summarize what it is in the original input sequence. And we reduce the length to a shorter sequence, and then we can input the shorter sequence into the large language model. So the model can handle this shorter sequence. Then we effectively extend the available context window. So in the next research, which is published earlier this year, we collaborate with the architecture and design department to solve the hallucination problem. So with long sequences, there's one problem with large language model is that if you ask it a problem that requires a lot of reasoning, it may not be able to give you the correct answer. And right now, there are some techniques like retrieval augmented generation. Then you can use this RAG technology to search or to retrieve the relevant information, but it is incapable of giving you the correct reasoning. So what we did is that we combine these two methods. We did some RAG, and then we asked the large language model to do more reasoning and combine reasoning and retrieval to have better performance in terms of hallucination and long context reasoning. Next, I will be talking about perception-centered image and video compression communication. So for this, we have some example applications like graphic games and VR and AR. This requires high quality image and video with less bits. So originally in Shannon's theory, when we talk about distortion, we mean like per letter distortion. But recently, there has been this drive for high perceptual quality. In this picture, we can see that if we want to constrain the perception to be the perceptual fidelity to be high, then we can have a visually pleasing reconstruction of the image. But this distortion may be very high because it changed the numbers. So this is the original or the traditional redistortion problem where you have an input sequence. You want to have some lossy reconstruction. It tells you that the redistortion is the minimum of the mutual information given the distortion constraint, which is a per letter distortion measure. But inspired by some recent advance in machine learning, we can have this neural compression system which measures which is trained by minimizing the difference between these distributions. Also, with generative modeling, we can generate new images from the decoder's end. So it has the same semantic meaning, but maybe in terms of the per letter distortion is very high. So these are optimized by minimizing the distribution between the source and the reconstruction. So in our case, we use this. We define the perceptual measure as distance between the two distributions instead of the per letter distortion. So we have this system model where we have we model common randomness and common site information as this so-called semantic knowledge base. So we actually have the coding theorems in this paper, and we proved the rate distortion perception function here as well. And I will be briefly talking about the generative modeling for semantic compression. So in this paper, we use diffusion model to generate better image better perceptual quality image. And we also design a hybrid image transmission scheme. This is combining the digital transmission with the so-called JSCC, joint source channel coding. So we want to combine, we want to integrate machine learning techniques into the traditional digital transmission. So we have these two streams of data, and then combining these two, we can have better reconstruction. And then we have some RDP application, rate distortion perception application. It's called steganographic communication, where you want to send some secret messages by embedding the message into a video or into an image. And some applications includes digital watermarking and safeguard data. So this paper is submitted to the Transaction of Information Theory, so we hope to hear back from them soon. Lastly, I want to briefly talk about video compression using generative modeling. This is also using diffusion model to do compression better. So thank you very much for your attention. This is all I want to say, and if you are interested, we are actively recruiting students and researchers, so please do not hesitate to contact me. Thank you.
Thank you for your nice presentation on semantic communication based on language model and generative AI. Let's move to the next speaker, Professor Yuval Kasuto from Technion in Israel.
Hi, good afternoon. Thanks for coming. Thanks for inviting me. So this is a joint work with my PhD student, Yuval Ben-Hur at the Technion, and with Professor Yongjun Kim from PostTech, which is an organizer of this conference. So the topic of the talk is reliable distributed inference. So we all know that ML, machine learning, revolutionized many applications, like computer vision, and natural language processing, to name just two. But in parallel, researchers from our domain, from information and communication theory, are thinking how we can help back machine learning with ideas from our expertise. And one topic we identified that we can help is in distributed machine learning. And that talk is about that. So you probably heard of distributed training, which is already deployed in the cloud. And in that system, it's not just one machine, it's many machines that do the training. So from the perspective of the cloud, this is distributed, but from the perspective of the client, it's still a centralized model. Because after we finish training, the client sees a centralized model and sends its full data features in order to get inference. What we aim in this talk is about a higher level of distribution, which is a distributed inference. And in that model, the client is no longer sending its data features, but it sends partial inference to help the cloud do the inference. So data does not have to leave, the private data does not have to leave the client, and that's what we achieve. So there are three main advantages for distributed inference. One is lower communication, because the information content of the partial inference is much smaller than the sending all the data features, like full pictures or videos. The second is that we can share computation between the clients and the cloud. Basically, the clients can help in doing the inference. But the most critical potential advantage, given the grim situation today, is that we get higher privacy. the clients need not send their data to the cloud. They send something that is much less leaky in terms of privacy. With all those advantages, there is one main challenge, which is reliability. Now that we give clients, we ask clients to help us with inference, there may be reliability issues. Clients may fail or do something even worse. So we need to solve that, and that's the purpose of this work. Okay, to see how this relates to semantic communication, let's first see what's classical communication, and there were hints about it in the previous talks. So system A, as Shannon referred, is at the top, where we take an X. X is here the data features, like a file, a text file or image, and our purpose is to reconstruct X with high fidelity at the receiver. And of course, there is noise, so that's the challenge that Shannon started. In our case, we don't care about X itself. We don't want to reproduce X. We want to reproduce the semantic, which in this context is the inference result on X, which we denote by H, capital H. And notice that there are two steps here. One step is that we don't care about X. We send just an inference of X. But even that, there's another step. We don't care about the individual small h of X. We only care about the total, the final inference that we get from all the clients together. So we make two steps, and that's the actual semantic that we care about. Okay, so what we, in high level, what we aim here is to have a new layer, which we call ML reliability physical layer, which we'll add under machine learning. And the reason is that there is good work to do in some machine learning in the distributed way using ensemble methods. We don't want to replace and reinvent all of that. We just want to add what's needed to get reliability in distributed settings. And the two main tasks, inference tasks that we deal with is, one is binary classification and the other is regression. Okay, so let's start with the noiseless problem. We have distributed, so we have capital T base classifiers, which send some real number, which we can interpret as a sign and confidence level. It's sent to the central processor that aggregates all those partial classifications into a final binary value, which is the final inference on X. That's without noise. Now, when noise is added, those signals that the node send us, they get corrupted by noise. And if we don't do anything, of course, the quality of the inference will degrade. And the noise here we model as a Gaussian vector with zero mean and a covariance matrix capital C. So what we need is to mitigate this noise. And what we propose in this work is to have two types of mitigations. One at the transmitter, a vector G, and at the receiver, we have a vector A that is used for aggregating the noisy signals. And of course, for this transmitter problem, we have some constraint on power, this capital G. And what we want is to get the best function that we have here, F tilde, indexed by A and G, which are the results of the optimization that we apply to this problem, given the noise parameters. We had an earlier work also with Professor Kim, where we did only transmitter optimization, and here we have both, transmitter and receiver. Okay, now there's interesting work here, algorithms and analysis, but I don't have time to show them, so let's jump directly to the results. Two data sets. Our results are with the markers, and you can see some gaps of our optimized function compared to the non-optimized, which is all ones at both the transmitter and receivers, and you see some nice gaps, 5 dB at the left, 10 dB, closer to 10 at the right, so we do get some good benefit from this optimization. Now, a similar problem is for regression. Now, this is a harder problem. We don't just want the sign to get a class. We want to actually get F reproduce the function as a real output function. But it's a similar problem. Actually, the solutions are quite different, but again, let's jump directly. What we do is a similar thing. We have now only in the receiver those A coefficients that we want to optimize. Again, let's jump directly to the result. First, that's the motivation, why this is an important problem. Here you see a result of a sample function. This is the skewed sign that we see. Without noise, that's the black dots, and you see the regression is pretty good here without noise. But when we add noise, we get those red points that show significant degradation. So that's the motivation to apply the optimization, and the results of the optimization you can see here. Each curve here is a data set, different data set. On the x-axis, we have the SNR, how much noise we add, and on the y-axis, you see the percentage of improvement of the optimized regression relative to the unoptimized, non-mitigated regression, and the units here are relative to the MSE, the loss of the non-noisy model. And you see that we also here have big numbers. Now, in this work, we depart from the black box. So far, we use those base functions untouched. We basically take the state of the art from machine learning, don't touch them, and only add those A's and G's to help getting noise tolerance. Here, we depart from that. So we have a partial layered, some cross-layering here. And what we do, we take the state-of-the-art algorithm for ensemble machine learning on the left, and we modify it to deal with noise. We basically tell this algorithm what are the parameters of the model, of the noise, and thereby we improve its performance given that the system has noise. And here in this work, the classifiers are binary. That's a special case of what we saw before. And the channels are also binary, either the binary symmetric channel, which flips those values, or the binary erasure channel, which is modeling the struggling. Basically classifiers that are supposed to give us their answer, but they struggle, they don't show up on time, and then we want to mitigate that. Here too, we also optimize the aggregation coefficients. And again, let's jump directly to the results. So the classical ADA boost, that's a state-of-the-art in ensemble classification. That's the red curve. You see it degrades linearly as the straggling probability increases. And our mitigated solution, the algorithm that we modified, that's in light blue, you can see that it's a much milder decrease as a function of the gradation of the struggling. And finally, we had a similar problem where we modify the state-of-the-art algorithm for noise, in this time for regression. And for regression, we cannot use AdaBoost. AdaBoost is a classification algorithm. So we take the state-of-the-art here, which is called gradient boosting. And again, let's see some results. So first, the desired property of without noise of this gradient boosting, you see as we increase the number of base of clients that send us values, we improve the loss. You see the MSE drops in the black. However, with noise, something really bad happens. The red curve, if you don't do anything for the noise, we use the state-of-the-art algorithms, we see that not only doesn't decrease, but it shoots up. The red curve shoots up. However, our modified algorithm, you can see in blue, it does drop and then gets stable. So at least we don't suffer from increasing the MSE due to the noise. What you see in purple is the in-between, when we take our algorithm but apply it without noise, and you see at the bottom that we actually get the same, for that data set, we basically don't lose anything. We can just use our algorithm. Without noise, it will perform the same, almost the same, actually even a little better than the state-of-the-art. However, with noise, it will manage to combat the really bad behavior of the red curve. Okay, so talking about the future, there are many applications that we can think about to use that, but maybe the killer app, and maybe you can help in future work, is about neurons. Neuron is a similar system. It has some activations from the previous layer, then some maybe noisy. Let's say we implement it on some noisy hardware or in some distributed setting, and then we have the coefficient, the weights of the neuron in blue, and what we should do is add those yellow coefficients that are supposed to combat the noise. The reason this is not an easy problem is that first, it's neither classification nor regression. It's something maybe in between. There's some activation function there in the neuron. But the reason this problem is more challenging is that we don't care about this individual neuron. So far, we measured the performance for a single aggregation. However, a neuron is part of a network, so we need to have some global performance measure to see how well we do in mitigation the noise. So to conclude, basically what we show here is a proof of concept of how to mitigate noise in a distributed inference. There's basically infinite amount of other problems to solve after that, so we need your help. And if you want to read more, there's a list of papers here. You can ask Songwoo for the slides, and you can read more. Thank you very much.
Thank you for your nice presentation on distributed inference. Okay, let's move to the next speaker. Next speaker is the Rob Bashni, professor from the UIUC in US. Let's give him a big hand.
All right, thank you for having me. Thanks to Youngjun and Singo for inviting me. So in addition to my role at the university, I'm also the founder and CEO of a startup company called Kokri, which is focused on music creativity, and we'll see a little bit of music in this concert. So I think if you came for a musical concert, at least you'll have a little bit. Last year, I was on leave to serve at the White House. So I served in the National Security Council staff in our national government. And I wanted to start with that a little bit. So something I drafted when I was working in Washington was this joint statement on principles for 6G wireless, focusing on secure, open, and resilient by design. And this was adopted in February of this year by the governments of the US, Australia, Canada, Czech Republic, Finland, France, Japan, Korea, Sweden, and the UK. And this kind of argued for a variety of shared principles around research and development of 6G. And as we'll see, there's kind of these interesting aspects of semantic communication that can influence a lot of these questions. So security and privacy, like kind of Yuval indicated, can often be enhanced by semantic compression. Resilience, like Mehdi will kind of alluded to, can also be enhanced in certain ways by semantic compression and semantic communication. And even interoperability and openness have certain kind of roles that come from semantics. And so I just wanted to kind of put that forward as kind of something in the background to think about as we're building out these 6G systems. Okay, so what I wanted to focus on in the presentation is compression. And in particular, there's been a growing interest in using AI techniques for text compression, using a lot of these large language models. And this has kind of really taken off in the last 4 or 5 years. there's been a lot of work in building these large language models. This is one example that I developed myself many years ago. And this was, at the time, actually better than GPT-2. It was the first billion parameter plus large language model that was open source released. And even back then, it was actually reasonably good. So, you know, it was reasonably fluent. The prompt here is just the text in red, which was a made-up URL, and that was the text prompt, and then everything else was generated from that. And so you can think of this, again, like other speakers have kind of indicated, is an interesting way of doing compression. So you compress what you care about into the prompt, and then you transmit the prompt. And you can do even fancier things. You can take transformers, use their probability predictions to as part of arithmetic coding to do text compression and all kinds of things. Right? So, so this is kind of a standard compression problem. But what we want to think about here is actually semantic communication. And for those who are less familiar, this idea of semantics really comes from linguistics, where there's these different levels of understanding. And kind of syntax, the red circle, focuses on phrases and sentences. Arguably, that's the focus of traditional information theory. Whereas the focus on meaning with semantics and the focus on contextual meaning with pragmatics really pushes that forward. And when linguists of meaning, linguists who study semantics and pragmatics think about it, they often argue that to study semantics of natural language is to study cognitive psychology. The human element is super critical. As we think about what it is that people will care about, as we think about kind of the notion of what loss is and the fidelity criteria of semantic communication, it should be very kind of human-oriented. Okay. So I think everyone who starts a talk about semantic communication often starts with this quote from Shannon. And what Shannon said in his original work in information theory in 1948 was that frequently the messages have meaning, that is, that refer to or are correlated according to some system with certain physical or conceptual entities. And these semantic aspects of communication are irrelevant to the engineering problem. And so what he essentially argues is that everything inside the block diagram is part of communication and everything outside of the block diagram is irrelevant. People often use this to kind of dismiss Shannon's approach, right? They say, oh, I mean, you should definitely consider the semantics. And that's been kind of the motivation for semantic communication in recent years. But I wanted to point to a couple other quotes from Shannon that kind of give you kernels of things that that indicate that Shannon was actually thinking about meaning quite seriously. So one is the fact that many of you might not realize, but Shannon was one of the founders of the field of artificial intelligence. So the 1956 Dartmouth conference that really got artificial intelligence started was organized by Claude Shannon and 3 others. And in fact, Shannon himself believed that the most promising new developments in information theory would come from work on very complex machines, especially from research into artificial intelligence. And so there's this idea that, in fact, a lot of Shannon's later work, whether it was building this maze with this mouse Theseus that could automatically solve it, which was, in a sense, a form of reinforcement learning, or his work on chess-playing machines or other things, in a sense, were experiments in the information theory of artificial intelligence. Okay. So this is kind of one piece we want to keep in mind, that AI is part of information theory in a sense. Okay. The second thing I wanted to point to was what he spoke about at the 1950 London Symposium on Information Theory. So this is the program from that conference. And we can see that his talk was entitled The Lattice Theory of Information. And what Shannon put forth in the lattice theory was this idea of information elements. So you'll notice this came out just 2 years after his seminal work that established information theory. And the basic idea in the lattice theory is the following: that when you translate, say, a sentence from one language to another, from English to Korean to Morse code, as long as the meaning remains the same, it's saying the same thing. And so there's a kind of invariance, and that real kind of the core meaning is what is critical to communication. And the way this was mathematized is that Shannon put forth this idea of information elements, that these things are more general than random variables. And so if you have two random variables that induce the same sigma algebra, that they're informationally equivalent. And if you can kind of do that, that is kind of very powerful. So you should be looking at these information elements as kind of these basic units of semantic information rather than random variables like we do in more traditional information theory. And so, so this is kind of what leads to our work in this area. So we've taken the lattice theory of information that Shannon put forth in 1950, together with ideas from artificial intelligence, and we've built this kind of set of techniques that we call information lattice learning. So Shannon assumed that the probability measure is given. We're going to be learning it from data, but then we can use all the kind of mathematical techniques that come from it to do more things. Okay, so this is some work that's been led by my former student, Haizi Yu, who's also one of the co-founders of Kokri. And so in his PhD work, what Haizi showed was that if you develop this information lattice learning technique, which is very different than neural networks, it's much more energy efficient. I think someone expressed this concern about AI being very energy hungry. In fact, information lattice learning is at least 5,000x less costly than a big transformer in terms of energy. It's also very human engaging, directly human interpretable, and so on. And so what Haizi did was he trained a core lattice on the basis of just 300 chorales by Johann Sebastian Bach. And this actually learned about 75% of the University of Illinois music theory curriculum in the same human interpretable form as a textbook. So very human understandable. We know exactly what was covered, what was missed, what was not recoverable due to the nature of the input. And the same basic lattice structure, which was developed using isometries, which are a way to understand symmetries from group theory, was also useful for learning the laws of pattern formation in the genetics of neurodevelopment. And so I would argue that these kind of laws of music theory or of genetics, and the same thing works for chemistry and for quantum optics and various other fields, is kind of a conceptual abstraction. That these kinds of abstractions are the core of what semantics are. And so, so this is really powerful for knowledge discovery. It's also very powerful for generation. So let me just play you an example of how one can kind of abstract things like rhythm and melody and then develop new songs. So this is the original Happy Birthday song. Great, so I'm going to take the melody and harmony from Happy Birthday. This is Mozart's Piano Sonata K545. Okay, so I'm going to extract the rhythm from Mozart's K545, and this is these extractions are going down the lattice. Now I'm going to take these and I'm going to go back up the lattice to realize a new song. This will have the harmony and melody from Happy Birthday, but the rhythm from Mozart. Oops. Right, so hopefully everyone can kind of feel the harmony and melody from Happy Birthday, but the rhythm from Mozart. And I mean, this is one of the simplest of examples. If you're interested in playing around with this technology even further, I'll show you the website for the startup, and you can sign up for a waitlist. Okay, so so you can see that we've kind of semantically abstracted these key ideas of melody and harmony from one song, the rhythm from another, and then recombine them. And so that's really kind of a powerful thing that one can do. Oops. Sorry, I think I messed that up. Right, and so the core idea of information lattices is that you can construct what's called a partition lattice. This idea that there's kind of symmetries that you can look at invariances of. And I'll dig into the math of this tomorrow. But there's kind of this nice lattice structure, and as I was saying, going up and down leads to abstraction and realization. So you can see the vertical lines here correspond to things that you can compare. And so at the bottom, you can't compare anything. Everything is abstracted into a single unit. On the other hand, at the top, each thing is treated separately. Okay, so I'll dig into this a little bit more next time. And so what we argue is that this information lattice approach is kind of a very natural mathematization of semantic compression. And in particular, lossy semantic compression is equivalent to abstraction. This abstraction process of learning laws of music theory or extracting rhythm and so on is a form of lossy semantic compression. And I would argue, in fact, the very natural way to do it. Again, just to give you an example of this, so suppose you have a bunch of shapes. So you can abstract them in different ways, like based on color, based on convexity or concavity, based on number of sides. And so at the bottom, you have all the shapes abstracted into a single group, a single concept of shapes. But as you go up and down, you can see that you might split based on number of sides, like trigons, or based on convexity or color. Or you could have red trigons or blue tetragons and so on, right? And so as you go up, you're realizing more details. As you go down, you're abstracting more. And so you're kind of having loss as you go down, but in a semantically meaningful way. And you can do the same, for example, for music. So you can start with a full sheet music, and you can drop certain things, like you can drop the rhythm and just, drop the pitch and just keep the rhythm. Or you can drop the key information or various other things. And so this is a way of going downwards as you're lossily compressing in a semantically meaningful way. As it turns out, partition lattices have a nice correspondence to group codes in source coding theory. In particular, permutation source codes have a nice equivalence to the symmetry group in group theory. And this allows us to actually prove certain nice properties, which I'll get into next tomorrow. In particular, what one can prove is that information lattice learning representations, once they're combined with group codes like the permutation source codes due to Jelinek, Wolf, and Berger, can achieve the rate distortion limit for all these problems, for point-to-point settings, for successive refinement, and for multiple descriptions problems under semantic fidelity criteria. So this is really amazing that we can literally achieve the rate distortion limits for these problems that are especially important for wireless. So successive refinement and progressive transmission is exactly what you need for wireless settings. So we're quite excited about this general framework of thinking about abstraction and concepts as a natural language for semantics, and then also the ability to achieve the information theoretically optimal performance. And then it's also very instrumentable. I mean, as I showed you, you can implement information lattice learning and permutation source code. So you can literally do all of this as a way to do semantic communication. Right, so I'll stop there. And as I was mentioning, if you're interested in playing around with the music example, you can sign up for a waitlist on the CoCree website. And then I'll get into the mathematical details tomorrow.
Thank you, Rob. I think your talk seemed to be very interesting, and we will have a further discussion tomorrow. Okay, that is the end of the invite talk. We will have a 10-minute break, and after that, we will continue our panel discussion. Thank you. Okay, this is the panel discussion. Each panelist will discuss some free topic about the semantic communication and smart mobility. And let's starting from some right question. So we want to know each country's 6G research trend. So I want to ask the first question to Professor Rikuyandi. How about Finland? Finland 6G research trend.
Okay, so in Finland we have a program funded by the government through Business Finland called 6G Bridge. But in terms of investments, it's actually quite interesting that these traditional Nordic countries that are strong in mobile, they are investing very little to 6G. compared to, for instance, Germany that is investing a lot. So our program is relatively modest in size. It is very much sort of industry driven, so basically what Nokia is doing. So, and maybe not very innovative. So it's like, because then what is happening in the industry is that it's the mobile operators needs that tend to dictate what is done. And there are, of course, there have been, even in 5G research, there have been many things that have been discussed about the verticals, but they are, okay, maybe there's still research on those, but they tend to like realize very slowly or not at all, because the mass market is in this enhanced mobile broadband, and there is not that much happening in that domain right now. In terms of frequencies, it's when the 6G research started, there was discussion about terahertz and things like that, but now it looks that the main interest is in mid-bands, maybe below 30 gigahertz, and actually even more the lower bands, like around 6 gigahertz. So in terms of technology, what is needed is maybe just, I mean, you could take the 5G standard and have a change the local oscillator or the RF filters and be done with it. So, but yeah.
Okay. So I know that Finland is the very friendly country for South Korea, because you had lots of this research project with some Korea university. So how about this day? Still keep going on there's another funding for joint project from Korea and Finland?
Yes, I mean, we have recently had some Business Finland and Research Council of Finland, so these are the main funding instruments. Both have had specific calls for collaboration. So the Business Finland is like funding mainly like industrial research, whereas the Research Council of Finland is more academic research. And then in EU level, there is also some, like just recently there was one application round for specifically 6G research project in Korea, which we are now about to start now.
Okay. Okay, thank you very
that's-
much. And I want to ask this question to Mehdi, because the University of Oulu is very famous for 6G flagship. So how about the activity 6G flagship, and what is relevant to the semantic communication?
Yeah, so we started our kind of world's first 6G program back in 2018, and it runs for 8 years. So we are almost until the end now. So yeah, so basically at that time, of course, people thought we were crazy because 5G research was still happening. Now fast forward, everybody is looking into 6G. So yeah, so we looked at various technologies, of course. If you ask my personal opinion, I'll piggyback on what Riku said. Yeah, there is pretty much nothing revolutionary, whatever that means, except maybe my bias, yeah, on the semantic communication track, because it kind of challenges a lot of theories, ways of designing network, and so on and so forth. So this was a journey. I mean, for me personally, I started in 2021, and it's still learning so much. It's a topic which is highly multidisciplinary, right? So yeah, that's what I can say. But now we are talking about phase 2 of flagship. And there's a new kid on the block, like I was telling you, which is emerging, I don't know, maybe because of geopolitics or COVID, which is resiliency. I anticipate that this will be now kind of the major KPI maybe for distinguishing at least 5G from 6G, because it becomes quite clear, yeah. But other topics are, of course, also of interest, yeah.
Okay. Let's move to the Yuba. So how about Israel? Because Israel is very famous to defend the research. How about the communication research, especially for 6G and semantic communication?
Okay, so I'm not in the defense business, so I cannot answer that. But I think that for 6G, when you read the needs that it quotes there, I come from coding theory. That's my native field of research. We need more flexible codes, because in the previous standards, you had like discrete, some rate compatibility, some discrete states. We need some more, a richer menu of codes that you can switch easily between them. We need shorter codes that do well, and also codes with feedback. Because if we talk to a robot, it's not like talking to a base station. We need some feedback, and the code should accommodate those advanced modes of communication. Also, Mehdi mentioned in his talk that some applications can do with losing some packets. I agree with that, but we need models for that. In order for coding theorists to solve a coding problem under that constraint, we need some good modeling of what can we lose without any damage, and then we need to design codes for those models. So I think if standardization committees want to help the academics, they should come up with concrete models for all those future needs.
Okay. I will move to the question to Rob, because the U.S. is the technical leading country in the world, but I'm not very sure about the communication, because the recently the top paper and something like this kind of the result comes from the Asian and some European country. So how do you think? How about the research trend in the U.S. for communication?
Yeah, so as I mentioned, on the policy side, I think there's a growing interest in kind of openness and interoperability. One approach that people talk about, of course, is the Open RAN architecture, but there's related architectures, and this general idea of kind of technical standards being done on a kind of even playing field. So that's on the policy side. I think the cybersecurity and more broadly the security of wireless systems is of front of mind for a lot of people. In terms of once one does do the disaggregation of the wireless stack, I think that opens up a lot of research questions that are of growing interest in the US, because a lot of things can become virtualized or softwareized, as it were, whether it's radio access network design and those RAN intelligent controllers, or actually throughout the stack, even with adaptive codes like Yuval was just mentioning, or pretty much everywhere. And similarly, like with respect to security also, this kind of disaggregation gives you more surfaces that might be open to attack, but it also gives you much more visibility on what's happening. So if one has a monolithic system from Ericsson or Nokia or Huawei or whoever, it's hard to know what's going on in the middle. Once it's separated, you can see what's going on, and so then there's a lot of new research questions on security as well. I think there's still continuing interest in physical layer things, whether it's intelligent reflecting surfaces or terahertz or all those kinds of things. Yeah, I mean, I think broadly there's still a lot of interest in the deployment of AI within wireless systems. So, I mean, I think there's broad interest throughout the US in a lot of these problems, and I think going forward there's kind of a renewed interest.
Okay, thank you for your answer. And let's move to this question to the Xiaoyan. So I want to ask your personal thinking. So how about the research in the mainland China? Because the mainland China seems to be main source of the wireless communication research paper. There are so many papers coming out in the mainland China and Hong Kong and something like that. So, but some people criticize that it's just a paperwork. It's really far from the real practical system. How do you think this kind of the opinion?
Thank you very much. That's a very good question. I also see a lot of paper coming out about communication. Yeah, so as a disclaimer, first, I don't have a background in wireless communication, so I majored in mathematics during my undergrad study, and then I moved to optimization and operations research. So I don't really know much about wireless communication, and I also don't publish in those venues.
I'm not asking you.
So, yeah, and in my personal opinion, I think right now a lot of research are driven by this AI or artificial intelligence, and I think that's a trend in terms of semantic communication, where as we see, we already have this very good system, like communication system with 5G. We already achieve high capacity. So in the future, I think it's going to be more application driven. So there are a lot of application focusing on AI. So another aspect is that we can use AI to improve the current communication system. So these are two trends. The most paper I see are following these two trends. So that's my personal opinion.
Okay, thank you for your answer. And then let's move to the next question. So I wonder somebody are talking about the semantic information theory, because the information theory is the key foundation of the communication system. People are trying to extend this idea to the semantic communication. But in some sense, most of the semantic communication designed by the AI, recently LLM and the generative AI, but it's a little bit far from the information theory thing. But my question is that how information theory can contribute to the design of the semantic communication. I want to ask this question to Rob first.
Yeah, I mean, I'm an information theorist by training, and I'm a big Shannon fan. So, I mean, clearly, I think there's a strong role for information theory to play. I think some work in this area of so-called semantic information theory has been fairly naive. So it's just looking for synonyms, and that's about it. So you just reduce the alphabet size, and that's what some papers argue. But I think there's a much deeper thing to think about. So the information lattice approach that I was describing, I'm of course biased, but I think that is very much the natural description of it, and it also implies algorithms, learning algorithms like the information lattice learning and so on that would be directly applicable. I think the other dimension of this that might be a place where information theory can contribute quite significantly is with respect to energy efficiency. Information theory, as everyone knows, is really about how do resources translate into capabilities. Right, that's really the core of information theory and establishing those fundamental limits. I think some insight from information theory can also help with the question of what's the most energy efficient way to do semantic communication, or related questions. Likewise, there's these interesting papers starting to come out that bring together things like energy harvesting or simultaneous energy and information transmission together with semantic communication. I think those are actually quite interesting and a place where information theoretic thinking can help. Also with respect to architecture. So many people would argue that the key contribution of Shannon's 1948 paper was the separation theorem, the separation between source coding and channel coding. And that architecture has been, and the notion of bits that came out of it, has been critical to all technological development in the last 80 years. So if there's similar architectural principles that can come out from semantic information theory about separation, about modularity, about energy efficiency, I think all of those can be quite useful.
Okay, thank you for your answer. Okay.
So I just want to give a historical note. So we all know the 1948 Shannon paper, but notice that it took 18 years until 1967 for probably the first algorithmic realization that allows to communicate reliably. That's the Viterbi algorithm. So I think when we talk about the present, we also need to be realistic, given that timeline. It takes a lot of time to move from a nice theoretical framework to something that works and can be deployed. So I think my advice for the present and the future is to go look for some very deep model or deep models for semantic communication, and slowly let the community develop them into something workable. And don't try in one paper to solve a problem end to end until you beat some existing model, because it's a long run. We are going to a future of AI. It will not be in the next 5 years. It will last decades forward. So we need to be equipped with good models to push us all the way and not just to the near term.
Okay, I want to ask the Mehdi about this kind of thing. So you mentioned the world model when you are talking about the system to AI. So I remember the world model is the presented by the Jan Likun, the Meta, and so he mentioned that current LLM and generative AI is not the world model. They need to be innovated. So could you explain what is the world model and what is the relevant to the system to semantic communication?
Yeah. So this world model is not of those buzzwords. So in fact, I mean, the word world model is not new. It has been looked at by, Schmidt-Huber in the AI community, I don't know, maybe 20 years ago, maybe. So that was within the context of model-based RL, right? So, in reinforcement learning, either you learn a policy in the state space, so just, straight state action to action state, without taking into account the state transition dynamics. So when you do model-based RL, that model there actually quantifies those state dynamics. So that area was there, disappeared. We did model-free, deep neural networks explosion came. Guess what? We realized it doesn't generalize, not robust. We are back to model-based. Now, this is where it gets a bit tricky. So for Jan Lequin, now he doesn't want to probability transition in the state space, in the raw state space. Instead, what you need to do, you need to learn that transition in the latent space. Could be a space of your tokens if you want, right? And it allows you now to plan. To plan, for example, if you're autonomous driving, obviously, there's no storyline from a pixel, at time t, a pixel value at time t plus 1. You need to do some sort of look-ahead prediction, and that semantic space where you would do that, you have to learn it from data. I mean, it's a very basic idea. So Jan Lequin came up, is very vocal, too much, I would say, with this idea of joint embedding predictive architecture. It's called JEPA, which is high school stuff. You take X and Y, and now you want to compare whether X is Y are the same. Now, when you compare them, you don't compare them in the, let's say, pixel space, you compare them in the semantic space. So I think there's nothing new there. Of course, I mean, this forces us maybe to look at planning and reasoning. So as I was telling you in this kind of cartoonish brain, you have the perception module, right? But then, of course, in the brain, you have perhaps the system 2 module, which is, I mean, I don't know in terms of physical entity, but that's where you reason. So you have this knowledge base, perhaps, you know how, for example, if you're driving now, right, you're running some simulations. Basically, if there's a cliff over there, you know you're not going to go there. So you're simulating the effect, and you avoid doing that instead of a model free where you would go, hit the cliff, die, So this is actually the world model. Now, of course, from wireless communication, this is very important because we go beyond perception type problems, which perhaps are solved to some extent, okay? A lot of works on inference, perception action loop, there's this free energy principle, a lot of works there. So now it turns out that we need to also look at planning. LLM showed us that they hallucinate because they don't have knowledge of the world, right? So there are tricks for example, using RAG or some other stuff. So also have Benjio from the AI community is very keen on this idea. He has this notion of GFlowNet, generative flow networks. Same concept. Basically, instead of encoding in one neural network, both the inference and the world model, you do a modular approach. So inference is just for decision making, but you make sure that those decisions satisfy the rules of the world somehow. So I mean, this is basically the world model in very short. So how do you learn it? So for example, right now we know how to do it for text, images, but for video we don't know. So there is something called VJEPA by Jan Lequin. In fact, it's a hack. You know in advance what transformations are invariant, so use it to compress, right? But there's nothing kind of right now that goes beyond that. Yeah, but
okay.
So it's actually, so those guys are doing semantic compression, although they don't use that word, because now what they want to understand the kind of the law or the rules of the game, where the game is really what the video sequence is all about. Yeah.
So my next question is that if the world model is given, so what is the role of the wireless communication? And the wireless communication can contribute to design the world model? That is my question.
Yeah, so depends on your question. Do you want, for example, you have different robots. Of course, now you want to maybe learn a global world model in a federated learning manner. So yeah, maybe that's one setting, right? So in other words, they have their shared experience. They share it with the server. The server aggregates all this their local world model, right? And then you see what I mean, right? But from a wireless perspective, this allows you to do. So planning means that you avoid transmitting information, for example, to the receiver, right? So you would do that only when you know that maybe your world model is outdated, right? So you kind of decide to query it, right? Instead of just transmitting. And then it depends on the use case, right? For autonomous driving, you must have it, right? For collaborative robots, right? So perception alone cannot do it. You need to go from, let's say, perception to planning, then you feed back your action. So kind of a cycle, right? This is basically the need or the benefits of world models. To me, that's essentially the key piece, ironically or interestingly, of what AI is going for. And I think for communication, we need the ability to plan, reason, do look ahead prediction. So in which latent space are you going to do it, right? This is where I see it happening. Yeah.
Okay, so I understand that this is to design the world model, communication and sensing and something like that. Everything is combining,
Yes.
right? So
Yes.
I continue this question to the Professor Yanti. So you mentioned that your semantic so backscatter communication can be integrated semantic communication. So from the sensing perspective, what is the definition of semantic you made in your talk? From the sensing perspective, what is the semantic there? So there are so many definitions of semantic. So what is a semantic from the sensing perspective? What should we do for communication research? That is my question.
Okay. In that context, the semantics is like that. Normally, you are just estimating the channel, and you don't know anything where the reflection is coming from. So basically, now you have a reference point. So there is like now you know that certain multipath components are somewhere in the physical space. So that context and information can then be applied in either in the sensing process. So for instance, if you know that, okay, this multipath component comes from this wall or whatever, it could provide you some additional information about, for instance, the wall materials that you could utilize then in the future processing. That is like, so if it's combined to sensing as such, then as I mentioned, the mobility aspect is one, that location. So you basically embed information about the environment to the channel estimation, so you become kind of aware where you are.
Okay. So then let's move to the application part. So as I mentioned, this BrainLink X-ray update topic is the semantic communication for smart mobility. But could you explain what is the main challenge to realize the semantic communication for real mobility systems, such as autonomous driving and something like that? So I want to ask this question to Xuyen.
Yeah, thank you. So the question was
So what is the main? So we have there are so many semantic communication research, but I think that it's not enough to apply this technique to the real autonomous driving and some inter-robotic system for smart mobility. So what should we do to realize this kind of thing?
Yes, so demand is a very big thing in industry. So you have to have those demands to build better system to suit those demands. So as I see, one of the demands is that we have these video games, as I said in the presentation. So right now the demand is on like video transmission or image transmission with high quality. So for that we need very large bandwidth with low latency. So this is one demand for us. And in the future, as I can see, with AI, we can have more applications. Like in the future, as Professor Bennis or other professors also talked about, we will probably be in a situation where the machines have to talk to each other, right? like in those smart factory or in other situations, autonomic driving systems, we have those machines communicating to each other or machines communicating to human beings. So for that, we need to design our communication system to better suit this situation, which means we need some kind of translation between machine language and human languages. Thank you.
So I want to ask this question to you, Bob. So one of my concern for apply the semantic communication to the smart mobility is some latency, because usually current semantic communication designed by the end-to-end manner, transmitter receiver, but in the real mobility scenario, the situation is fast, it's a change fast, then there's out of distribution is happen frequently, then it is not easy to train the transmitter receiver in the end-to-end manner. So as I mentioned, as you say that it could be better to split the network, not in the end-to-end manner. So from that perspective, could you explain relevant, should you share your idea?
Yeah, I think I mentioned in my previous answer that we need some layered schemes. So one thing we developed in our group is a code that is LDPC code. LDPC is low density parity check codes. These are like the most deployed codes in the industry, both in communication and storage. But what we added is a feature that we can we can decode only a sub-block. Let's say the channel is actually good. We don't need all the redundancy of the entire block. It's enough for us to use one sub-block to get our information. But we still have the bigger block with more redundancy in case the channel is not as good. And for example, in an automotive environment, it's a highly variable quality of the channel. So this layered approach to design codes help us deal with those variable environments, that we get the best of both worlds. We get the high reliability of the long blocks and the low latency of the small sub-blocks. So I think that type of heterogeneity and layering can really help in those more advanced environments.
Okay, thank you for your answer. So next, my last question is that some safety issue of the smart mobility. So semantic communication can be understood as an effective technique, but I don't think it's not very reliable technique because it's designed by the neural network, something like that. So in order to design semantic communication more reliable, what should we do? That is my last question. Rob, do you have any answer?
Yeah, so I completely agree with you. The critical infrastructure, whether it's transportation, water, energy, any of these, it's super important that we make these systems not only smart, but also safe and secure. And I think there's a variety of questions related to this. One is ensuring that there isn't things like hallucinations from the AI components, that there isn't kind of acting crazy in settings where there's no training data, like kind of overconfidence and kind of acting weird in unknown unknowns. There's also ensuring security against things like data poisoning and so on. Another key aspect of this is also ensuring the appropriate privacy. So when one does deploy these smart cities technologies, there's often a concern that one is creating a surveillance state. And ensuring that one does this in a way that protects civil rights and civil liberties, I think is super important. And with respect to how does semantic communication play into this? I think it can really help because when we're drawing on things that have kind of knowledge-driven ideas rather than purely data-driven ones, I think it's a nice way as kind of a fallback when data doesn't help us, when we're in situations that we don't know what's going on. Likewise, I think semantic compression can help with these concerns about civil rights and civil liberties as well, because one can compress to the minimal thing that's needed to accomplish the task rather than transmitting everything. So I think there's a variety of roles that these ideas can play, especially as we build out these so-called smart cities technologies in a way that respects people's rights and liberties.
Okay, thank you very much. So it's almost time is over. So we want to receive some question from the audience. So you have any question?
I have one question about information lattice. So my question is this: in machine, then what are the main and distinct differences between information lattice and regular extracted features or representation learning?
Yeah, I suppose I should answer this given my expertise in it. Yeah, so information lattices are directly human interpretable. So when you construct the partition lattice, you have an explanation for all the rules that are coming out in terms of group theoretic invariances. So you know exactly why a rule is what it is. And so that is a key difference than, say, neural network techniques or similar techniques, because of the human control and human understandability. A second kind of key difference is that there's even the learning process itself is very transparent. So, I mean, not just the results, but even the learning process itself is super transparent. It's kind of the student-teacher architecture, which allows you to know how things are developing. And then there's a variety of other kind of advantages. One is in terms of things like training data and intellectual property. So, like I mentioned, like the lattice in the music case was trained on just 300 chorales by Bach rather than stealing and scraping the whole internet, which leads to a lot of uncertainty about what is this even trained on. So it's super well curated because it requires very small amounts of data for training. And also, I mean, there's energy efficiency. It's much more efficient. It runs on CPUs rather than GPUs, which is nice from certain perspectives and so on. So, you know, there's a variety of differences in human control, human interpretability, intellectual property rights, energy efficiency, and so on.
Yeah, just I may add what Lav has said, because we're looking also at this notion of information lattice, for example, in the context of multi-agent communication, right? So this idea of kind of organizing your data. So this could be, take a sensor, right? It's sensing the world at different resolutions. If you want to draw the space of all the possible, let's say, state, whether discriminate one state, two state, or maybe two states are equal because they induce the same partition, you end up exactly with the same lattice structure, he said. But also you could apply the same principle for models, because in fact what we shouldn't live with one model. We need a library of models, and we could see one model is probably going to be maybe a refinement or partially refinement of another one. So you end up with kind of a nice category, right, or library where you can store different versions of a model, and then depending on your abstraction level, depending on your latency, reliability constraint, you select the right abstraction to solve your task. So instead of having, let's say, no structure, meaning all models are equivalent, right, here we're trying to kind of say one is better than the other, right? So what is that algebra? What do you mean by this one is better than that, right? Is because they maybe induce the same level of the abstraction, or one is better, right? Just to add that.
So do you have any other question? Okay.
I have two questions, but because of the time limit, I would like to make it shorten to the Professor Yanti. Yeah, I always dreamt about the smart city with ambient backscatter devices, but I think that is one of the key points of the security. I mean, is it better than the RFID? Because maybe someone can take a look at all the information. Also, they can manipulate the data system. So sometimes I wonder if it is possible to make it more safe. So I would like to ask the things.
Yeah, I think that is one of the critical questions. What I have been discussing even with some industrial partners on this application. So, there is a need to be able to authenticate the devices and to avoid this kind of repetition things. Actually, RFID is not that great either in terms of security. So, so what we are currently working is physical layer authentication schemes. Those are kind of the only option if we have extremely simple devices that don't even have receivers. Once we have a receiver there, then we can start to, in the backscatter device, then we can start to do something more, slightly more clever, but they are still very resource constrained devices. So it's kind of a hard research problem how to make it. And it's also a trade-off. So on the level of security that you want to have, you can make it very secure, but then you are consuming a lot of resources. Like if you need the full receiver there, and with then that is consuming so much power that the whole point is lost.
Because I'm one of the late person who is on LTE 4G, because I think that the speed-wise, the faster speed will take more information within a quick shot. So I always wonder that if the speed gets better and better, there will be more the vulnerable point on those data security things. So thank you.
Okay. So any other question? Okay, that is the all of the today's panel discussion. I'm very happy to share our discussion to the audience, and from the tomorrow we will have a much in-depth discussion for semantic communication and smart mobility. In the future, I hope that we have a more opportunity to share our thinking to the all audience. Okay, that's all over today's program. Thank you.